Alright, so in this video we are going to talk about some applications of Newton's second law beyond equilibrium and introduce a few other concepts and ways to apply Newton's laws. Okay, so let's just focus on Newton's second law in some examples. Okay, so we'll start with the idea we already know or recognize net force is mass times acceleration. Okay, that's Newton's second law. And the important thing to see here is that, again, we talked about how forces describe how objects move, or rather, why they move. Forces describe how an object moves. Okay? And then once we know how or why they're moving, so I apply a net force and this is what caused it to go into motion, we can then go from there and figure out, well, how does it move? Okay, and the idea here is we're taking forces and we're using that to find an acceleration. Okay, and then once we know acceleration, that leads us into kinematics. Okay, and so all of this together represents a field in physics that we simply call dynamics. Okay, so dynamics can be broken into a few things. The first one was what we covered in the last video, and that was the idea of equilibrium. Okay, now we already said equilibrium was when the net force is zero, and this happens one of two ways. The first way is a way we call static equilibrium, okay, where static essentially means we're at rest. So static is at rest. And the other type is dynamic equilibrium. Okay, and so dynamic equilibrium would be that you're moving, but since you're at equilibrium, it means you're moving with constant speed. Okay, so that was the first thing. That's what we focused on in the last video, was this idea of equilibrium. We're going to classify it into two different ways now. And then the other way to look at it is, well, what if the object was not in equilibrium? So what if there is net movement on the object? All right, so here's an example we can use from that. So let's imagine we have a box on a frictionless surface. Okay, this box has a mass of, say, 10 kilograms, and we apply a couple forces. Let's say one force is to the right of 50 newtons, another force to the left of 25 newtons, and so the question is, what is the acceleration of the object? Okay, so using Newton's second law, we've got net force equals mass times acceleration. So remember, net means total. So on the left side here, what we want to do is total up all of our forces. We've got 50 newtons minus 25 newtons gives us the mass, which is 10 kilograms, times the acceleration. So when we work this out, we find the acceleration is going to be 2.5 meters per second squared. Okay, so it's nothing too difficult, nothing you can't mathematically do, but the setup is different. Now we're talking about, we only have one equation to start with, and that is Newton's second law. So as long as you can total up the forces acting on an object, you can then find out how much the motion is changing. Okay, that's our acceleration. And then once we know the acceleration, we can ask numerous other questions. We can ask how fast after some time, how fast after some distance. Okay, the point is we can then go into kinematic world. Once we know the acceleration and we're holding these forces constant, we can then move into kinematics and kind of go back to all the things we've done earlier. Okay, now there is one force that we need to make sure we talk about a little bit. Okay, if we look at this picture that we have drawn here, I only drew two forces, 50 newtons to the right, 25 to the left, but there's a couple of others that we've kind of ignored when doing these problems. because the object has mass, it is definitely being pulled down by a force due to gravity. And because it's touching a surface, there is definitely a force, normal force, working against it. Remember, normal force is the force perpendicular to a surface. Okay, but you'll notice that when I wrote the net force out, I didn't include them. Okay, and there's reason for that. Just like we did with vectors and two-dimensional motion, the reason they're not included in here is because the 50 and the 25 Newton forces were along the x-axis. Okay, if we were to look at the y-axis, then we've got another net force going on here. We've got normal minus the force due to gravity. Okay, technically for Newton's second law, we would write the net force is equal to ma, but we already know the acceleration because up, down, so because of up, down, it's not moving. So not moving up, down, we know the net force up, down must be 0. Okay, and so that's mainly the idea of doing a free body diagram, which we can make, the dot instead of the object, but the forces work in 2 dimensions, and so we need to make sure we outline all the forces in all dimensions. Okay, so one of the things I want to focus on is gravity. So force due to gravity. Okay, so you might have seen this in a problem, or I might have done this in a video, but the idea is that if we want to find a force due to gravity, okay, it's a net force acting on an object. So let's back up a step. You have an object here, say a ball, and the ball is free falling. So we know that it has an acceleration of negative 9.8. Okay, and remember g is the acceleration due to gravity. That close to the Earth's surface is 9.8 meters per second squared. Now, the only force acting on the ball is gravity. So if we set up Newton's second law, so I'm going to do that back over here, where the net force equals mass times acceleration, the only force acting on it is gravity. And that force is equal to the mass times the acceleration, which in this case is free fall acceleration, or g, 9.8. So it follows from this that anytime we want to find the force due to gravity of an object near the surface, so this is force due to gravity near the surface. Okay, and that last part's important, but we won't go into more details on that until a few more chapters. Okay, but when you're near the surface, we can equate the force due to gravity as always being the mass times the acceleration due to gravity, 9.8. Okay, and so this has something to do with another number that we're familiar with. Okay, that number is called weight. Okay, so what is weight? Well, let's start with mass. Okay, it's important to understand that mass and weight are not the same thing. Okay, hopefully some of you already know this, but it's important to state it. Okay, mass talks about how much matter is contained in an object. Okay, and the important thing is that this number doesn't change. If you go to the moon, you have the same amount of mass that you do on Earth. Okay, but then weight is an effect. Okay, and this is gravity's effect on your mass. Okay, now, and that's not the only thing for it. Okay, weight is also a reading on a scale. Now, here's what we mean by that. If you stand on a bathroom scale and it says that you have a weight of some number, say 100 pounds, okay, then if you were to take your hands and push yourself up on the table, that number decreases. Okay, your mass hasn't changed, the force due to gravity hasn't changed, but how much you're pushing down on the scale has changed. And so effectively the weight measurement has changed. Okay, so essentially we say that weight is not necessarily a force. Weight is a measurement. Okay, weight is a result of weighing something. So if you have an object that's stationary, right, let's say that I've got a scale here. Okay, and typically how scales work is we put the mass on the object, or excuse me, the mass on the scale, and gravity tries to pull this thing downward, but because it's touching a surface, there's a normal force push back. Okay, now inside the scale, you have these springs. Okay, and so as the springs are compressed, the scale gets a reading out of that. And so the idea is that if this is at rest, it follows that the normal force is equal to the force of gravity, which we called mass times gravity. And so the normal force is just the reading on the scale. Okay, and as mentioned, then weight is the effect of weighing something. It follows that this reading on the scale is what we call the weight. Okay, so it follows that when we look at the weight of an object, that weight is equal to the mass times gravity. Okay, but hopefully you can see from here why they're not the same thing. So again, if I go to a different planet, right, if I go to the moon, right, the mass will not change, but the gravity gets weaker. Okay, so if the gravity gets weaker, there we go. Okay, I'm sorry. So on the moon, the gravity gets less. Okay, because moon gravity is much less than Earth's gravity. So if that means there's less of a gravitational effect on my mass, again, the mass hasn't changed, it follows that the weight on the moon is much less than the weight on Earth. So mass and weight, not the same thing. That's important. Okay, that also brings us to an idea of something that's called weightlessness. Okay, an object that's weightless. So how does one become weightless? Remember, weight is an act of measuring or weighing something. So how do you become weightless? The idea of weightlessness means that an object is in free fall. Okay, essentially there is no normal force. Okay, there is no normal force that's providing a weight measurement. Even if I were to put this object on a scale and allow both the ball and the scale to enter free fall, since the scale is falling at the same rate as the ball, there would be no normal force, and therefore there is no weight measurement. And if there's no weight measurement, then that means there is no weight. So therefore we call it weightless. But it doesn't change the fact that there is still a gravitational force that we can calculate to be the mass times the gravitational effect. Okay, effectively in free fall, you're weightless, but it doesn't change that gravity is still trying to pull you down. Okay, all right, so let's go into one more application on forces, and this one gets to a little more seriousness in forces. Okay, and so it's the idea of putting something on a ramp. Okay, now you might think, well, how does this change? And it's kind of simple. You imagine a simple inclined plane, so typically drawn as like a right triangle. Okay, and this incline has some angle to it. Okay, now we take an object, say some random box, and we put it on this surface. Okay, and there might be friction, there might not be, but let's start off with no friction. Okay, so we're going to add in here that there is no friction on this ramp. Okay, so once we incline the ramp, and since there's no resistive force, this box is going to start to slide down the ramp. Okay, but what is effectively pulling it down the ramp? Okay, and the answer is gravity's doing something, but it's not all of gravity. Okay, and this is the part that we have to understand. Okay, so if I were to make a free body diagram of this, well, first let's draw the forces on the picture. So let me get rid of this blue arrow, because I don't want you to mistake that for a vector. Okay, and so now let's draw the vectors that are acting on this box. So if it has mass, then gravity is definitely trying to pull it down. Okay, since it's touching a surface, there must be a normal force. But remember, normal force, okay, normal force is perpendicular to the surface. So if the surface is inclined at an angle, it follows that the normal force must also be inclined at an angle. So my normal force would be at a right angle to the surface. And right now, these are the only two forces. Again, we said it was no friction, so these are the only forces that would be acting on the box. So how much force is actually trying to take it down the ramp? Okay, and so that brings us to another important point. When we're doing ramp problems, it's usually good practice to say that your axis of motion is down the ramp. That means the y-axis is perpendicular to the ramp. So we tilt our axes here. And the reason we do that is if you look at the direction of motion, right? So this dashed yellow line, drawn over in blue now. Okay, if you look at that line is going down and to the right. So if we wanted to calculate the acceleration, that means there is an x acceleration and a y acceleration. So we'd have to find two accelerations. That means the net force in both the x and the y are not zero. Now, that's not an impossible problem, but it's definitely not fun to do. So we do not want to have that situation. We want to make at least one of these net forces zero, and the other one have an acceleration that we can solve for. Okay, so let's get rid of these components because we don't want that. We want this to be straight down the ramp. Okay, so how do we do that? Let's start with a free body diagram so we can clean this up. So here's the object. The normal force was up to the right. Gravity is straight down. Okay, we said the x-axis is tilted slightly. That makes the y-axis on the normal line. Okay, so the idea is we want to take this diagram, and if it's easier to see, we want to rotate it ever so slightly so that now we have the normal force going straight up. Okay, we have this dashed line that represents the x-axis, the rest of the y-axis going down, and you'll notice that gravity is at an angle. Okay, it turns out that the angle of the ramp is located right with gravity and the y-axis. Okay, so we're going to draw gravity on our new diagram. And we put the angle with the y-axis. Now the geometry to do that is not too bad. I don't want to waste the space and time to do it here. So if you're curious, you can ask me in class. But for right now, just go with it. The incline of our ramp is always drawn with the y-axis. Okay, so what we want to do to solve this then is you want to break this into the components that go parallel to the x-axis and parallel to the y-axis. Remember that the force due to gravity, which we just found, was mass times gravity. Okay, so how much of this force would be on the x-axis, rather this horizontal component? Well, if you look at it, the angle, where the angle's drawn, the horizontal part, this flat part, is opposite to the angle. So it follows that on the x-axis we would have the hypotenuse, which is mg, times the sine of the angle. And then on the y-axis side, since that's adjacent to the angle, we would have mg cosine. Okay, and now this is always true for ramps. So now we can redraw our diagram. We had normal force straight up, and we don't need to draw the yellow weight line because we've already broken it up into components. We have mg cosine going into the ramp, basically, and then we also have mg sine, whoops, not f, mg sine going down the ramp. And since there was no friction, there are no other forces on the left side. So here's our free body diagram. Okay, so from here, if we wanted to solve for, say, the acceleration, so what we would do, and it's kind of like we wrote in the last problem and what we tried to, or what I wrote at the beginning of this problem, you have to split your net force into x's and y's. Okay, so in the x-axis, all we have is mg sine theta. Okay, and again, Newton's second law says that F net equals ma. Keep in mind, this is an x acceleration. And on the y-axis, we have normal minus mg cosine of the angle is equal to, it should be ma, but keep in mind that the box is only moving down the ramp. It's not moving along this vertical line. It's not moving in the direction of the normal force. So therefore, that net force must be 0. From here, we can then solve for whatever we want to solve for. What I want to do is quickly take attention to the x-axis, because if I solve this for the acceleration, I've got mg sine of the angle is equal to ma, and some quick algebra steps. The m's go away, and we find that the acceleration down a ramp when there's no friction is simply equal to gravity times the sine of the incline angle. That's important. And until we bring in friction, this tells you exactly what the acceleration would be of an object that's freely sliding down a ramp.